Hello, my name is Kelsey Prantis, Senior Software Engineering Manager of the DAOS Development Organization here at Intel. Today I'm here with you to share some performance of the DAOS software stack as it's running on the latest generation of Intel Xeon Scalable processors, as well as the Intel Octane Persistent Memory 200 series. Several years ago, our HPC team here at Intel began to tackle the challenges found in Lustre scalability. Being experienced with mass-scale deployments, we could clearly see the limitations of file system performance scalability for big installations. As storage media had evolved over the years with SSD technologies, these limitations came mainly from the file system software stack, rather than being limited by the storage media technology themselves. The fundamental limitations of the legacy storage software stacks became even more obvious later when much faster, non-volatile memory technologies appeared in the market. There were several bottlenecks in the legacy software stacks, but the most prominent of these are the POSIX interface and block-based I/O. To ensure data consistency, the definition of the POSIX interface requires pessimistic locking, proactively locking in any situation where a conflict might occur. Imagine if tens of thousands of clients were writing to the same file and the amount of serialization that would occur if locking on every relevant operation, even if none of those writes would actually generate a conflict. This pessimistic approach just does not scale. So it became necessary to consider other ways to provide data consistency to unlock the file system for future scalability. DAOS instead borrows techniques from the database space to utilize optimistic concurrency control, eliminating the need for so much locking and delivering higher performance. Similarly, all persistent I/O up to this point has been done on media that we write to in large-sized blocks. This poses a real performance dilemma for I/Os smaller than the block size, including file system metadata, as small I/Os sharing a block would then be cause for more locking and serialization of activity and less parallelism. But this could not be solved with software alone, but needed a cooperative change with both software and storage media in order to overcome. Intel Octane Persistent Memory is a fundamental technology that DAOS builds upon. DAOS is designed from the ground up for performance, combining persistent memory and NVMe SSDs with direct access through the PMDK and SPDK user space libraries to talk to the media directly, and providing a high-efficiency software stack on top of that with rich functionality attached over RDMA-enabled fabric. Unlike SSDs, Intel Octane Persistent Memory offers low latency byte granular access, which means that applications can now access small pieces of data in parallel, free from the locking required by blocks. DAOS takes advantage of this by storing two different types of data in the persistent memory, metadata as well as small I/Os, which is defined by the DAOS policy engine. This allows us to optimize bulk data writes to NVMe SSDs for better SSD performance, where higher block size delivers better bandwidth and SSD endurance, which is dependent on the write pattern. This enables our customers to use less expensive SSDs, such as moving from high-endurance SSDs to mid-endurance or to standard endurance drives, or even moving between technologies such as TLC-based NAND SSDs to QLC SSDs. Breaking through these barriers would never be possible without this storage hardware innovation. The transition away from SATA to NVMe and the appearance of persistent memory, as well as coordinated software stack innovation, including new ways to access data in user space, defining new interfaces such as key value, HDF5, MPIIO, and a Python API, while maintaining a legacy POSIX interface to ease the transition. All DAOS I/O operations on the critical performance path involve Intel Octane Persistent Memory. So having a product of the next generation with improved performance can be easily translated into performance improvement of the entire software stack. Let's dive into a few of the key features of the Intel Octane Persistent Memory 200 series that helps drive improved performance. With gen over gen performance improvements of the Persistent Memory 100 series versus 200 series, we can see an up to 32% average improvement for random 70-30 mix operations. To start with, the new server platform design, which is based on the third generation Intel Xeon Scalable processor, significantly improves overall memory bandwidth by providing 8 memory channels instead of the 6 provided on the prior generation. It's important to note several improvements in the PMEM module design and their contribution to DAOS performance. The greatest improvement comes from the module speed, growing from 2,666 megatransfers per second from the previous generation to 3,200 with the full 2 DIMM per channel population. Also, in the past, data had to be flushed from the processor caches using the flush command. We've added a new platform-level capability called EADR. In a platform that supports the energy store needed, EADR allows the platform to take care of flushing the data from the processor's caches so the program doesn't need to do it itself. This allows DAOS via the PMDK to eliminate a point of synchronization and be able to deliver more IOPS. Finally, the overall server platform has a better I/O subsystem by introducing PCIe Gen 4 support with 64 lanes per socket. We leveraged this capability in our demo configuration to use a 200 gigabit InfiniBand fabric, and this could be utilized further to take advantage of a PCIe Gen 4 SSD, though we'll not be demonstrating the SSDs today. So how can we measure this performance improvement? Well, for HPC storage, we have a good set of tools designed to stress various aspects of it, such as metadata, file I/O, chunk size, and overall scalability by leveraging multiple clients. IOR and MD test are two commonly used benchmarks for this. They are different by design, and it's often required to use both for a complete storage performance assessment. These benchmarks form the foundation of the IO500 storage performance list. MD test is designed to stress the metadata performance. It's quite common in HPC to see parallel access to many files opening for reads, writes, attribute updates, creation, or deletion. On a big scale, those operations can create a significant bottleneck in the file system performance as they typically cause locking, though this locking is minimized in DAOS. MD test measures how quickly you can serve those operations. IOR, on the other hand, measures throughput performance. Unlike MD test, IOR is dealing with I/O operations, such as reading and writing into multiple files simultaneously using many clients. This is where actual bandwidth is measured across many files simultaneously from many clients. For DAOS performance analysis with persistent memory, we considered both benchmarks to be critically important, being representative for the overall file system performance and providing clear guidance recognized by the industry. Let's take a look at performance numbers of a DAOS instance based on the second generation Intel Xeon Scalable architecture with Intel Octane PMEM 100 series versus the Intel Octane PMEM 200 series running in a brand new system design with Intel Xeon Scalable third generation processors. Each test cluster has one DAOS server and 2 compute servers. Each system is dual socket and fully populated with PMEM and have 2 200 gigabit NICs on a Mellanox InfiniBand fabric. The third generation CPUs have 36 cores each, while the second generation have 24 cores each, and we use 1 MPI process per hyperthread. So in the demo we're sharing here today, we're running 3 benchmarks from the IO500 suite in a loop. We start with IOR Easy with a single shared file and a transfer size of only 64 kilobytes. IOR Hard doing 47,008 billion interleaved I/O, and MD test to benchmark POSIX metadata by creating, statting, and unlinking empty files. First, let's look at our IOR Easy results. As I just noted, we're using only 64 kilobit I/O size, which would be considered small by other storage systems that typically consider 1 megabyte plus as typical I/O. We do this to demonstrate that DAOS can deliver a very high throughput with relatively small I/Os. Writes show significant performance gains thanks to the additional memory channels on the third generation CPUs, as well as higher bandwidth per DIMM in the 200 series compared to the 100. For reads, the improvement primarily comes from the PCIe Gen 4 support in the third generation CPUs, allowing the 200 gigabit fabric to deliver the full PMEM read performance. Overall, the third generation platform is able to deliver an average of a 50% performance gain over the second generation platform. Now, let's look at our IOR hard results, which is called hard for a reason. Traditionally, other storage systems struggle greatly with these workloads, seeing up to 100 times degradation of performance between hard and easy. But for DAOS with Intel Octane persistent memory, you can see we can deliver comparable performance for both the hard and easy workloads with a degradation of less than 10%. Lastly, let's look at our MD test results. You can see here that the third generation platform can deliver over a 1 million file creation rate and a 1.7 million file stat rate with just a single server and 2 clients. This is a significant improvement over the second generation platform, which would require more client nodes and MPI tasks to deliver the hardware performance, as the third generation platform brings more cores per CPU. We are very excited about the performance gains that DAOS is able to achieve with the third generation of the Intel Xeon Scalable processors and the Intel Optane Persistent Memory 200 series. And I'd like to thank all of you for joining us here today and allowing us to share this data with you.